Hi everyone, and welcome to Chapter 4, Lecture 2. This is going to be all about reactions in solution. So we're going to be looking at the different types of reactions that we can perform that are in aqueous solutions. So in Chapter 3 we looked at reactions like synthesis and decomposition, where we're looking at maybe solids and gases, maybe even liquids. Now we're talking solely about aqueous solutions. So you have learned many different reactions, but we have examined only a tiny fraction of the millions of possible chemical reactions. So to make sense of all of these reactions, we need some sort of system in order to classify and group all of these reactions. So these three categories are those that are used most by practicing chemists. So we have precipitation reactions, acid-base reactions, and oxidation reduction reactions. Now, oxidation reduction, or more commonly known as redox, is all about electrons, so losing or gaining electrons. We're going to talk much more about redox later, about chapter 20, so second semester, but for now all you have to know is that oxidation reduction is all about transferring electrons. Double replacement reactions, which is probably what you are more familiar with, is an overarching type of reaction. And under double replacement reactions, we actually have two subsets. We can have precipitation reactions or exchange reactions. Now, a lot of times these are one and the same, but there is a chance that one is a little bit different, and we're going to look at that a little bit later. So in a double replacement reaction, typically we have two solutions that contain soluble salts, and we mix them. So again, notice that it's always in solution. In a double replacement reaction, our positive ions switch, and in a precipitation reaction, we have what is called a precipitate form. It's that solid that falls out of solution, kind of like snow out of the sky. Now, when we have a precipitation reaction, we can actually separate the precipitate from the filtrate, which is the rest of the solution, in a process that's called gravimetric analysis. So again, that's gravimetric analysis, and you guys are actually going to be completing a gravimetric analysis during the school year. So take time right now, pause the video, look at the particle diagram on this screen as well as the double replacement reaction, and make sure that you are starting to remember how these work. To identify a precipitate in a precipitation reaction, you must know your solubility rules. You can find the solubility rules table in your summer packet. It's also in your book, or it's on the screen here. You will be expected to know that all potassium, nitrate, ammonium, and sodium salts are always soluble. So again, potassium, nitrate, ammonium, and sodium. Now you can also look at these solubility rules, and it's going to be expected that you know all of these. But it is also important to know or to distinguish between the phrase slightly soluble and insoluble. Now, slightly soluble means that a small amount of solid that dissolves is not noticeable. So what that means is when you look at the beaker, it doesn't look like the solid dissolved. So typically, slightly soluble and insoluble can be used interchangeably. You have in the resource videos on the class website a video that's titled Precipitation Reactions. Take a look at this. It's going to walk you through a precipitation reaction again, so you can see, you can take a look at the solid being formed. So pause the video right now, watch this, maybe make some extra notes from that video, and write down any questions that you have. So as you're working through double replacement reactions, there are some special notes or some exceptions that you want to make sure that you know, and it would just help if you memorize these. So the first one is H2S, okay? It is a gas that will come out of solution. So really what you need to do is know that H2S is a gas. If you look at the example right here, you have HCl and Na2S. Well, when your positive ions switch, you get H2S and NaCl. So again, important for you to know H2S is a gas. Also, you want to look at carbonic acid, sulfurous acid, and ammonium hydroxide. These are all unstable when they are in solution. So if you form H2CO3 in a double replacement reaction, it's important that you know that it breaks down into CO2 and H2O. So you're never going to even write H2CO3 as a product. You're automatically going to write CO2 and H2O. And then that's the same for sulfurous acid and ammonium hydroxide. As you work with double replacement reactions, it's going to be very important that you know how to not only complete the reaction, but also to balance the equation. So some steps to follow as you go through. The first is to use the chemical formulas to figure out what you have present. Okay, write your formulas for your products. So your positive ion switch, make sure that you crisscross charges and you balance out those charges using the proper subscripts. Then you want to check your solubility rules. If either of your products is insoluble, that means that you have a solid that forms. And then finally, balance the equation. So as you write these double replacement reactions, there are actually 3 different ways that you can write them, and all show something different. The first is the molecular equation. Okay, the molecular equation is actually the overall balanced equation that you're probably used to seeing. Then we could write the complete ionic equation and the net ionic. So the molecular is going to be the most broad, the net ionic is going to be the most specific. So the molecular equation lists the reactants in the products without indicating any ions. So this is the overall balanced equation that shows the reaction stoichiometry, but not the forms as they exist in solution. So all we know here is that both of our reactants are in solution and that our potassium nitrate is a product that is in solution, but that's as far as we go with the molecular equation. This is, again, important for you to do stoichiometry. Then we get a little more specific. So then we have the complete ionic equation. In a complete ionic equation, this represents all of the reactants in the products that are strong electrolytes as ions. So what that means is any strong acid, strong base, any soluble salts are dissociated into their ions. This actually reflects what is in the reaction mixture. So the complete ionic equation has all of the ions as they exist. And once we get even more specific, we can write the net ionic equation. So to form the net ionic equation, you're going to cross out anything that does not change from the left to the right. Think about it like canceling out variables. If you have x on the left and x on the right, you can cancel those out. Now the net ionic equation includes only the components that are undergoing a change. Spectator ions are not included. So those ions that you cross out are your spectator. These are the ones that are not involved in the reaction at all. Spectator ions start as ions, they finish as ions. And so what this means is down here we crossed out nitrate and potassium on both sides. If we wanted to rewrite this, we could rewrite it Ag plus aqueous plus Cl minus aqueous yields AgCl solid. Notice this is also balanced. This is our net ionic equation. This is actually showing what is happening. It's showing the chemistry behind this reaction. And so there's always a conservation of mass and charge in net ionic equations. This is how every chemical reaction that you write in AP must be represented. AP wants net ionic equations. It does not want molecular. So get used to writing net ionic equations whenever you have a double replacement reaction. So again, here's just a summary of writing net ionic equations. First, write and balance your molecular equation, break down all strong electrolytes, cross out anything that's the same on the left and the right, and it has to be the exact same. It has to be Ag plus on the left, Ag plus in solution on the right to cancel out. Then you write the net ionic equation with anything that is left at the end. So we looked at double replacement reactions, and now we're going to focus on acid-base reactions. Now, like I mentioned before, we are going to have 2 entire chapters devoted to acids and bases, but this is just a general overview of these types of reactions. So in an acid-base reaction, we have an acid, and it is donating a proton to a base, and what happens is they neutralize each other. Okay? If they react completely, they neutralize each other. When the base has a metal hydroxide, we then can form water and salt. Now, salt does not necessarily mean sodium chloride. Salt is any ionic compound. So if we have HCl and NaOH, we form H2O, which is water, and NaCl. In a neutralization reaction, each reactant, which is an acid and a base, is neutralized. So what this means is if it goes to completion, all of the H plus reacts with all of the OH minus. But the pH is not necessarily 7. The pH of the salt formed actually determines the pH of the solution, and we'll discuss more on this later, but it is important to remember that the pH might not necessarily be 7.0. Now notice at the bottom here we have a net ionic equation for this neutralization reaction. We have H plus OH minus gives H2O. And notice that H2O is a liquid. Anything in a net ionic equation that is solid, liquid, or gas must stay together. We cannot break water down on the right-hand side because it is a liquid. Only aqueous solutions can be dissociated into ions. Yet another type of reaction is those that form gas. So some exchange or double replacement reactions do not give what we expect. This goes back to the H2CO3 being unstable. So when a carbonate reacts with an acid, that means that we form salt, carbon dioxide, and water. This also was in your chapter 3 reaction notes, so make sure you look back at those chapter 3 notes. You have to have all of those memorized. And finally we get to the oxidation reduction reactions, which again for you, all you need to know right now is that it has to do with transferring electrons. So single displacement reactions are one type of oxidation reduction reaction. In a displacement or a replacement reaction, the more reactive element replaces the less reactive element in the compound, and this is where the activity series comes into play. So if you look at this reaction at the bottom here, notice again it's a net ionic equation. We have solid copper reacting with silver ions in solution, and we get Cu2 plus and Ag solid. So the reverse reaction though does not occur. So I want you to kind of think about why the forward might occur, but the reverse might not. So as we work through single replacement reactions, it's important that you know how to use the activity series. So the activity series is a list of metals that is in order of reactivity. So at the very top up here we have lithium. Lithium is going to be the most reactive. If lithium is by itself and you react it with something in a compound, lithium is going to kick that other metal out and going to replace it in the compound. The metals at the top are very active. The ones at the bottom are least active, and that's going to be the way that you're going to go through these single replacement reactions. Now, you will not have to memorize this activity series, but it would be important for you to just kind of look at what's at the top of this. Notice that it's group 1 and group 2 metals. Those are the ones that are more reactive than some of the heavier metals at the bottom. Now, going back to the last slide, we were talking about copper, so let's write it down here, reacting with Ag plus in solution. Okay, and this forward reaction took place. This forward reaction, we had Cu2 plus and Ag solid. So the forward reaction worked. Okay, what that means is you have to look at the metal that is by itself, right? The solid metal. Is copper more reactive than silver? Yes, if we look up here, copper is higher than silver. So this copper is going to kick silver out of solution, and that's how we get these copper ions and solid silver. This is actually how you can electroplate silver onto different items. Now, I asked if the reverse reaction worked or not. Well, this is why the reverse reaction doesn't work. If you look at silver, which is the metal, needs to be more reactive than copper, which is in solution. If we look here, silver is not more reactive. Silver cannot kick copper out of solution. So that is why the reverse reaction does not work. And again, as you're working through these single replacement reactions, you could have a metal reacting with acid. So a very common example is magnesium ribbon being dropped into HCO. So Mg solid reacting with HCO, which is aqueous. Now, in this case, you look at your activity series. Is magnesium more active than hydrogen? And the answer is yes, because what happens is you see bubbling, which is H2 gas, and then we get MgCl2, which is in solution. And then you could go through and balance this. But any elements that are above hydrogen, like magnesium or any other group 1 or group 2 metals, they will react with acid to produce hydrogen gas. Now, when it talks about the metal being oxidized, we can just kind of ignore this for now. But what happens is your metal actually goes into solution. And then we could rewrite this as net ionic by breaking HCl down and breaking MgCl2 down. And then you would be able to see the overall net ionic equation for this. So just to briefly summarize, we went through different types of reactions in solution, talked about double replacement, precipitation, exchange reactions, as well as acid-base and single replacement reactions. Now, we also kind of mentioned gas forming. Please take a look at your Chapter 3 reaction notes if you have not. What you're going to find is I'm going to give you a lot of resources like that, and I'm going to expect that you look over them. If you find that you have questions, just let me know. Just send me an email. Really, as you work through any of this Chapter 4 material, if you have questions, feel free to let me know.